theorem, and we're using it right now to calculate deflections. In the next example that we look at, we're going to use it also to solve an indeterminate beam. So we can apply this method to solve for the reaction forces in an indeterminate structure. All right, but first we got to finish up this example. Right, we were looking at this cantilever beam with an applied moment at midspan, and we first went through and calculated the deflection at the free end by applying the fictitious force and then determining the moment equations in the two regions with the fictitious force in play. After setting up the integrals and then dropping the terms that have the fake force in it, evaluating those integrals provides the deflection at the free end. And now we were going to go and check that value using a different approach, right? Same method, but just a different approach. And so we got part of the way through that. We have determined what the slope is at midspan. And so next, if we determine the deflection at midspan, we can then use those two pieces of information to figure out what the slope should be, or what the deflection should be at the free end. So continuing with that process then, to find the deflection at the center, all right, so now the value we're interested in is delta M. We now need to introduce a fictitious force, right? Since we're interested in the vertical displacement at midspan and we don't have a force there, we need to add one in to set up the integrals. So we'll add that fake force there. Now we need to rewrite our expressions for moment in each region. So the moment in region 1 would be Fi times L over 2 minus x plus m naught. And the moment in region 2 would just be 0, because there's nothing happening after that midpoint. So then, applying our method here, the deflection at midspan is the partial derivative of the strain energy with respect to the applied force at that same location, right, which is our fake force, Fi. So we have 1 over EI times the integral from 0 to L over 2 for region 1. And then plugging in our expression for M1, we have M naught plus Fi times L over 2 minus x. And then we'll multiply that by the partial derivative of the moment expression with respect to Fi, and that is L over 2 minus x. And since M2 is just equal to 0, we don't have to bother with the integral for the second half of the beam span. So just evaluating this expression, we get delta M is equal to M naught L squared over 8 EI. So we can then project, knowing the displacement at the midspan and knowing the slope at midspan, and also knowing that the slope won't change between the midpoint and the free end, since there's no actual applied load between those points. We can say that the deflection at B should be equal to the deflection at the midspan plus the slope at midspan times L over 2, which gives us M naught L squared over 8 EI plus the slope at midspan, which was M naught L over 2 EI times L over 2, which gives us 3/8 m naught L squared over EI, which matches what we found previously.
I'm assuming you always draw that fictitious force in a positive direction just for simplicity.
So I've been sticking with that, but you don't have to. The only thing to make sure that you pay attention to is if you decide to draw it downwards, then a positive result will mean that your deflection is in the same direction as that applied force. So you just have to make that connection. Wait, so hold on. Let's see. I take that back because that's not consistent with what we just did. Let's see. So we look at that again. If I is not needed there. Actually, no, that is true. Yeah. And I was thinking of the wrong type of solution. So yeah, so what I said is true. So a positive result here, right, means that our deflection is in the same direction as the applied fake force, and that makes sense with this loading, right? A counterclockwise moment applied there would have the effect of sloping the beam upward, right? And so that also means, right, consistently a positive slope would be consistent with the direction of the applied moment, right, which is consistent with that upward deflection. And then the positive deflection at B is also consistent with that, because then that deflected shape would be something like that. So the sign of the resulting deflection or slope that you're solving for will just means that if it's positive sign, that means it's going to be in the same direction as the assumed force or moment that you used for that solution. Yeah.
You can have fictitious moments too, right?
You can, yeah. If we wanted to calculate the slope at B, then we would add a fictitious moment there. Or I mean, really don't have to, right? Yeah, because it's going to be the same as the slope here. So yeah, but yeah, you can add a fake moment as well. All right, let's see. Is that it for that page? I think so. All right, so now we're going to look at an indeterminate beam, and I'll show you how to apply this method for solving for indeterminate beam reactions. So this beam here is indeterminate by 1 degree. Let's say we want to find the deflection at the free end. So just say and we'll say goal is to find delta 3. All right, so since it's indeterminate by 1 degree, the approach we're going to take is to choose one reaction support, all right, so one resisting element, and relax it. And we're going to replace it with a force that would be in the same direction, but we're going to treat that force as an applied force instead of a reaction. So for this solution, at this example, I'm going to choose to relax the support at node 2. It doesn't really matter which one you choose. And we'll introduce a reaction force . We'll call it R2. All right, so now we draw a new sketch of our beam here. We have the fixed support, applied moment, M naught, the force R2, and then we also have reaction forces at the fixed end. And since we are looking for the deflection at node 3, we need to introduce a force at node 3 since there's not one there. So I'm going to choose Fi acting downward.
So R2 is you said we're assuming it's an applied force.
We're treating it as an applied force for this first part of the solution, yeah. Let's see, oh, I already wrote that line. What I want is this. So for delta 3, we'll apply Fi at node 3. All right, so when I was saying we'll treat that reaction R2 as an applied force, that comes into play in the next step. So we're going to write our equilibrium equations, but we're going to basically solve for the reaction forces at the fixed end that we didn't relax in terms of R2, Fi, and M naught. So we're kind of just treating that R2 as an applied force in our equilibrium equations. So from equilibrium, we'd have M1 is equal to R2L minus Fi times 2L minus M naught. And R1 would be equal to Fi minus R2. So the next step will be to write the expressions for moment in each span. So in the first span, x between 0 and L, we'll call that region 1, 2. So the moment in element 1, 2 is equal to the end moment, M1, plus R1x. And so substituting in these expressions for M1 and R1, we'll have our moment expressed in terms of all the, quote, applied forces that we're considering. All right, so say this first chunk here is M1, and this is R1x. For the second region, x between L and 2L, we'll say, call that M23, and that's just going to be negative M naught minus Fi times 2L minus x. So it's already in terms of only applied forces. We don't have to make any substitutions there. So now we're ready to apply Castigliano's theorem. So our strategy now is to solve for R2 in terms of M naught, Fi, well, ultimately Fi will be dropped, right? But we want to solve for M2 in terms of, or what did I say? We want to solve for R2 in terms of M naught and L, right? So then once we know R2, we can go back and we can find M1 and R1 just in terms of M naught and L. So we have all of the reaction forces then in terms of the applied, the true applied loads, right? So in order to do this, we're going to use the knowledge that at node 2, there actually is a support there, which means that the deflection at node 2 will be 0. Right, so we're going to set up our Castigliano's expression for the deflection at node 2, set it equal to 0, and that will allow us to solve for R2 in terms of the actual applied moment. All right, so for this portion of the solution, we actually don't need the fictitious force. I set it up in advance because we'll use it later. But we'll start here. So we've got delta 2 is 1 over EI times the integral from, for the first region, 0 to L. We'll have M1 to 2 times the partial derivative of M1 to 2 with respect to R2, right? So we don't need the fictitious force because we're taking everything with respect to the vertical force at node 2, which is R2. So then for the second region, we'll have 1 over EI times the integral from L to 2L of M23 times the partial derivative of M23 with respect to R2. Set that whole thing equal to 0. All right, when you go through this, you'd find this second integral is going to be 0 because the partial derivative of M23 with respect to R2 is 0. So you're only going to have contribution from the first region, all right? And as I mentioned earlier, we actually don't need the Fi term for this part of the solution. So solving that integral, we will obtain R2 is equal to 3 over 2 times M naught over L. Then we can write M1 as M naught over 2 and R1 as negative 3 over 2 times M naught over L from the relationships we outlined above. Questions?
Could you have used a different force than R2?
Not for the deflection at 2. Yeah.
Okay.
Yeah, so since we're starting with the deflection, oh, you mean for your up here, like when we chose to relax R2?
Yeah.
Oh, yeah. Yeah.
Whatever you want.
Yeah, absolutely. You could have chosen to relax the moment at 1, is essentially turning this into a pin support, and then you'd have R1 and R2 would be your reaction forces that you would solve for in terms of M1 and M naught. And then you would set these integrals up, and you would take the partial derivative with respect to M1 to find the slope knowing the slope here is going to be 0, right? You'd be solving for theta 1 equals 0, and this would be with respect to M1.
Okay.
Yeah.
What about like if we had two indeterminate by 2 or 3 degrees, we would have to relax multiple things?
Great question. I don't think I've applied this method to problems that are indeterminate by more than 1 degree. So yeah, I think you could probably do that. You'd end up with having multiple steps though. Like probably you'd have, trying to think of how the best way to do that would be. Yeah, I think it would still theoretically be possible. It would just be more work. Yeah. Yeah. Right. So now that we've found those reaction forces in terms of the true applied loads, our ultimate goal, remember, was to find the deflection at node 3. So I'm going to add that note that I verbalized here, because it's usually a point of confusion that comes back to haunt us later on. We'll just say Fi is not needed for this part. So finding the deflection at node 3, that's where we need the fake force Fi. I'll just say here is where Fi is needed. So for the deflection delta 3, we have partial derivative of strain energy with respect to Fi. That'll be 1 over EI times the integral from 0 to L of our moment in region 1 to 2 with times the partial derivative of M12 with respect to Fi. And then we have the second region integral from L to 2L. And that's all with respect to M23. And Fi. And so we defined those expressions for M12 and M23 before. Let's see, didn't we? Yeah, we did, up above. So plugging that in, we get delta 3 is equal to 0 to L, integral from 0 to L of, we'll have 1/2 M naught minus Fi times 2L minus 3/2 times M naught over L times X. So now I've substituted in what we know for R2, right? Because up above, maybe it would be helpful to rewrite those. Up above, we had M12 in terms of R2, and so plugging in this for R2 is where I'm getting this term here. So maybe I'll just note that. M1, R1, and R2, all in terms of M naught and L. All right, so we've got our M12. Now we need the partial derivative of that with respect to Fi. So that's going to be, let's see, I missed something. Oh, I did forget one term. All right, so in this bracket, we also have plus Fix. So the partial derivative is going to be x minus 2L. And then from the second integral, we have from L to 2L, say negative M naught minus Fi times 2L minus x. And the partial derivative with respect to Fi is 2L minus x. So at this point, we can eliminate the terms that have Fi in them.
Are we leaving out the 1 over the
Thank you. That should be in there. Yeah, so 1 over EI in front of both integrals. So solving for delta 3, we would get 3 over 4 times M naught L squared over EI. Okay, questions? Okay. So I'm kind of straddling lectures now in the schedule, but next up is the applying this to circular beams. So lecture 24. Definitely not going to get through this whole lecture today because it's another long one, as all the circular beam ones are. But we'll get started. So same concept, right? Same general approach and general method, just now we have circular beam equations and relationships to incorporate. So start off with the strain energy expression for a circular beam, right? We can write this as 1 over 2EI times the integral from 0 to phi of m squared r d phi, and that would be applicable for a thin circular beam. All right, so for a thin circular beam, that's something where you would have, you would assume that the variable radius, what am I saying here? You would assume that R is equal to capital R. All right, so it's not going to make much of a difference, the variable radius. We can just take it as the centroidal radius. So applying that, we'd have our normal stress in X is equal to M times Y over capital A, lowercase e, capital R. And we're going to set that equal to my over I, so that the product of A, lowercase e, and R is equal to I, or in other words, lowercase e is equal to I over AR. So then our strain energy is the integral from 0 to phi of m squared over 2a capital E lowercase e d phi, which we can rewrite as the integral of m squared over 2ei times capital R d phi. All right, so remember when we talked about circular beams and how shear stress is generally negligible. So going along with that, that follows that the moment distribution will be the most significant contributor to strain energy. So we'll look at an example for that scenario, and then we'll also talk about scenarios where you wouldn't be able to neglect certain things. I think that's in this lecture, or maybe it's in the next lecture. That's in the next lecture. All right, so that'll be later. Don't worry about that for now. All right, so first we'll look at this example of a quarter circle beam, and we're going to find the vertical and horizontal deflections at the free end, where there's also an applied vertical load. So again, since we're assuming the moment distribution is the dominant contributor, that means we can neglect all, remember that really long strain energy term for circular beams that we did last time? That means we can neglect the terms that have the V, the MN, and the N terms inside them for a thin circular beam. All right, so to start off, we'll just take a cut through this circular beam. All right, and then looking at the right side of that cut, summing moments, we'll get an expression for our moment equation. So the moment plus PR sine phi is equal to 0. Or M, and this is, to clarify, this is your moment. Now it's a function of phi, right? So M of phi is equal to negative PR sine phi. Now, this is, right, technically in this cut, we are also exposing the normal force, the shear force, as well as the moment. And then I'll break it the rest of that down too. So here's that moment arm, r sine phi for the applied force to that location. So just for the sake of completing the equilibrium equations, right, if we sum forces in the normal direction, we would get N is equal to negative P sine phi. And if we sum forces in the shear direction, we have V is equal to P cosine phi. All right, but I'm going to say for shear, we can neglect for circular beam deflections. They really won't contribute much at all. All right, so now, just as a good reminder, this specific equation isn't relevant to deflection, but always good to recall. The normal stress for a circular beam is my over I plus n over a, or in general, not just for circular beam, right? For circular beam, you have the other variables that show up. All right, so for our deflection calc, we're looking for the vertical deflection and the horizontal deflection at the free end. So first we'll consider the vertical deflection, delta By, and that's going to be the partial derivative of strain energy with respect to the applied force P. Since the applied force is in the vertical direction, we have that to work with. We don't have to add a fictitious force. So that's going to be 1 over EI times the integral from 0 to pi over 2 of the moment times the partial derivative of the moment with respect to P times capital R d phi. So that's 1 over EI times the integral from 0 to pi over 2. And then our moment is negative PR sine phi. And the partial derivative of the moment with respect to P is negative R sine phi. And then we have R d phi. So there's M. Partial derivative. So our delta By can then be written as PR cubed over EI, all of which are constant and can be brought in front of the integral. And then within the integral, we're left with sine squared of phi. Evaluating this integral, we get pi over 4 times PR cubed over EI. And so what direction is the deflection, the vertical deflection at B? Downward, yeah. So intuitively we can see it should be downward based on the direction of the applied load, right? Intuitively, without even thinking it through, we know that should be a downward deflection, but also since we got a positive result for our integral evaluation, that means it's going to be the same direction as the applied load. So it's going to be a downward deflection. All right, and then I'm going to add a side note. All right, so this is FYI, a little refresher on some trig calc. The integral of sine squared phi is phi over 2 minus sine of 2 phi over 4, and the integral of cosine squared is equal to phi over 2 plus sine of 2 phi over 4. All those fun math things. All right, so to find the horizontal deflection at B, now we do need to apply a fake force, Fi, because we don't have anything in the horizontal direction. So we'll add Fi in the horizontal direction. And then we still have those exposed internal forces at the cut. Here's the moment arm for the vertical load. Here's the moment arm for the horizontal load. Or sorry, actually the moment arm, since we're taking it about this point, is going to be this distance here, not that r cosine phi. Right, this is your moment arm here, 1 r times 1 minus cosine phi. So now we need to rewrite the moment expressions to account for that fake force. So we have m is equal to negative PR sine phi minus Fi times r times 1 minus cosine phi. And then setting up the integral for delta B in the x direction, we have the partial derivative of strain with respect to the fake force Fi, which is 1 over EI times the integral from 0 to pi over 2 of m, which is PR sine phi. I am preemptively getting rid of the negative sign because it will cancel out once we incorporate the partial derivative. So PR sine phi plus Fi times r times 1 minus cosine phi. And then the partial derivative, r times 1 minus cosine phi. And then we have r d phi after that. So this part is our moment. This part is the partial derivative with respect to fi. So we have delta bx is PR cubed over EI times the integral from 0 to 2 pi. Nope, pi over 2. Can't read my own writing there. Pi over 2. And then we're left with sine of phi minus sine of phi times cosine of phi inside that integral. Yep, more trig identities are coming your way. Sorry to break it to you. So here, integral of sine, of course, is negative cosine. Integral of sine phi cosine phi is sine squared phi over 2. So evaluating the integral with those trig identities, we get delta bx is equal to PR cubed over 2EI. Since we got a positive result, it will be in the same direction as the applied fictitious force to the right. All right, so I've got a few notes and then we'll call it a day. The actual physical moment, right? We have our equation here for a moment. The actual physical moment is just negative PR sine of phi, right? Because this doesn't exist. So just remember that. Also, keep in mind that we technically do have still a normal force and a shear force acting here. We just neglected them for the purposes of this deflection calculation because their contributions to strain energy are very small compared to the contribution of the moment. Questions?
Did you lose a negative sign when going from the moment equation to the deflection, or is that?
So I just preemptively got rid of it because it will cancel out, because you'd have, right, this would be negative and negative, but then this would also be a negative, so it would cancel out.
Okay.
Yeah. So I just cleaned it up and got rid of it. Other questions? I know we're over time, so I apologize, but thank you for your attention and have a great weekend. See you Monday.
Dr. Bennett, before you
Yep.
shut this down, can you scroll to the first page of this lecture?
Yes, we can do that.
I missed, yeah, some of this. Oh, not much. Okay. Thank you.
Yep,
Appreciate it.
you're welcome.
Where are you gonna be? We were supposed to be I'd rather read the letter too.